Have you ever stopped and wondered what's actually happening inside an AI's brain when it learns? When it goes from being totally useless to surprisingly smart? It can feel like magic, but it's not. It's just some incredibly clever math. So today, we're going to pull back the curtain and look at the core engine that really drives all of machine learning.
Okay, so let's ask the big question right up front. How does an AI actually learn? How does it go from getting everything wrong to getting things right? It's not just random guessing, right? There has to be a system. And there is. It's all about a process of self-correction. But to correct your mistakes, you first need a way to measure just how big your mistakes are.
And that's where this thing called a cost function comes in. You can just think of it as a how wrong are you score. If the AI makes a really bad prediction, it gets a high score, a big error. If it's getting close to the right answer, it gets a low score. So the entire game of training an AI boils down to one simple goal. Tweak all your internal settings to get that cost score as close to zero as you possibly can.
So really get this, let's use an analogy. Picture the AI standing on a massive hilly landscape, and it's completely covered in thick fog. This entire landscape is the cost function. Every single spot has an altitude, and that altitude represents the error score. The AI's one and only mission? Find the absolute lowest point in the entire landscape, the bottom of the deepest valley. The catch: the fog is so thick it can only see the ground right at its feet. So how in the world does it know which way is downhill? It needs some tools. It needs a compass and maybe even a map. And this, my friends, is where a little bit of calculus becomes our superpower. The first derivative, which in this world we call the gradient, that's our compass. It points exactly in the direction of the steepest downhill path from wherever you're standing. It basically screams, "Hey, go this way, it's downhill over here." Then you've got the second derivative, called the Hessian. Think of this as your terrain map. It tells you about the shape of the land right around you. Are you in a wide, gentle valley or on the edge of a steep ravine? Knowing the curvature of the land helps you decide how big of a step to take.
I love this quote here. It just nails it. The gradient is your speed and your direction. The Hessian, that's your acceleration. It tells you how the slope itself is changing under your feet. Put them together, and you have a seriously powerful navigation system. So, problem solved. All we have to do is calculate these derivatives. Sounds simple enough, right?
Well, not so fast. For really simple problems, yeah, it's a breeze. But when we're talking about the massive AI models we use today, these things have billions of parameters. Just calculating these derivatives becomes this absolutely monumental challenge. Let me show you what I mean.
Okay, check this out. For a basic function like this one, finding the lowest point is literally high school calculus. You find the derivative, you set it to 0 because the slope is 0 at the very bottom, and you just solve for your parameter. Boom, done. The perfect answer is 1.6. Easy peasy.
But here's the thing. An AI model isn't one clean, simple equation. No way. It's millions, or these days, billions of functions, all nested inside of each other, all interconnected. So the math to find the derivative for that starts to look a little more, well, like this. And believe me, this is still a super simplified example. This is for just two functions combined. Now imagine doing that for a billion parameters. The complexity it explodes.
So the old school methods just completely fall apart at this scale. You can't do it by hand, that's just insane. Using a computer to approximate the answer, too inaccurate. You get all these little rounding errors that throw you off course. And trying to get a computer to write out the full exact formula, that creates these monstrous equations that are so huge and bloated, your computer would just grind to a halt. We were stuck. We needed a better way. And luckily for all of us, there is a better way. There's this incredibly clever technique that's both perfectly exact and super efficient. And honestly, it's the engine that basically unlocked all of modern AI.
It's called automatic differentiation, or AD for short. And here's the genius of it. Instead of trying to tackle one giant impossible formula all at once, AD is way smarter. It breaks the entire program down into a long list of tiny simple steps, like add these two numbers or multiply this by that. It calculates the tiny little derivative for each of those tiny steps, and then, this is the magic part, it uses the chain rule to perfectly stitch all those little pieces back together. The result? You get the perfectly exact derivative you wanted, but you got it in this incredibly efficient way.
Now, AD comes in a couple of flavors. There's forward mode, which is great if you have just a few inputs and a ton of outputs. But think about our AI model again. It's the complete opposite, right? We have millions, even billions of inputs, all the model's parameters, and it all funnels down to just one output, that single cost score. We have a many inputs to one output situation. And for that, Reverse Mode AD isn't just a good tool, it is the perfect tool for the job. It's wildly efficient for exactly this kind of problem. And here it is. This is the big reveal. This powerful mathematical technique, reverse mode automatic differentiation, you probably know it by its more famous name, backpropagation. That's right. The legendary algorithm that powers all of modern deep learning, it's really just a specific, very clever application of this mathematical trick. It's the engine that's humming away inside TensorFlow and PyTorch, calculating those perfect gradients and telling the AI exactly which way is downhill, step after step.
So let me leave you with this final thought, because this is where things get really wild. This technique isn't just for neural networks. It's a way to find the slope of improvement for pretty much any computer program you can write. This idea is so big, it has its own name, differentiable programming. Just imagine being able to automatically optimize not just an AI model, but a simulation for discovering new drugs or a complex model for climate change. The idea is, if you can write it as code and you can define what better means with a score, you can use this math to teach a machine how to improve it, all by itself. And we are just scratching the surface of what that really means.